Good morning. Today we are going to derive the Einstein's field equation from variational principle. Consider two scalar densities minus root of minus g into r and root of minus g into lm. Here r is the Ricci scalar and lm is a scalar related to matter distribution. Now the invariant integral over the space-time volume V4. We are considering a four-dimensional space-time. Let the space-time be represented as V4. Then the invariant integral over this particular space-time volume can be written as I equal to integral over V4 root of minus g into r plus root of minus g into lm into d for x. Since we are considering a four-dimensional space, we are using d for x here. Now we consider a variation delta g mu nu of the metric tensor within the space V4 such that the delta g mu nu and delta g mu nu comma alpha, that is its derivative with respect to the index alpha, vanish on the boundary of V4. Now we can write the equation for delta I. Delta I will be integral over V4 delta of this minus root g into r plus root of minus g into lm into d for x. Let it be equation number 1. It can be written as integral over v. When you operate this delta, you will get delta of minus root of minus g into r plus delta of root of minus g into lm into d for x. Okay, let it be equation number 2. Now what will be the value of delta root of minus g into r? It can be written as delta of root of minus g. Now r is the Ricci scalar. Ricci scalar can be written as g alpha beta into r alpha beta. When you are contacting the two covariant indices of the Ricci scalar, you will get the Ricci scalar. So now there are three terms here, that is root of minus g alpha beta and r alpha beta. So when you operate this delta, what you are getting is first term will be g alpha beta r alpha beta into delta of root minus g. Okay, the first term. Then you can differentiate the second term. Then you will get root of minus g r alpha beta delta of g alpha beta. Third term will be root of minus g alpha beta into delta of r alpha beta. Okay, this can be written as g alpha beta r alpha beta is the Ricci scalar r, so it can be written as r into delta of root of minus g. There is no change for the remaining terms, that is root of minus g r alpha beta delta g alpha beta plus root of minus g alpha beta into delta of r alpha beta. So this is the value of delta of minus g into r. Let it be equation number 3. Now we are going to calculate each term. First we can calculate the term delta of root of minus g. Delta of root of minus g. What is the differential of root g? The differential of root g is 1 by 2 root g into differential of g. So it can be written as 1 by 2 into root of minus g into delta of minus g. Now, in the previous class, we have obtained the relation g of g mu nu equal to 1 by g dou g by dou g mu nu. Okay, this can be written as g of mu nu equal to 1 by g into delta of g divided by delta of g mu nu. So what is the value of delta g? Delta g will be equal to g into g mu nu into delta of g mu nu. Now we can substitute this value here, but remember here it is minus g. So what we are getting is 1 by 2 into root of minus g. Here it can be written as minus g into g mu nu into delta g mu nu. Now minus g divided by root of minus g equal to root of minus g. So it is equal to root of minus g divided by 2 into g mu nu into delta g mu nu. Now the value of g mu nu into g mu nu, that is the product of conjugate metric tensor and the metric tensor, it is equal to the dimension of the space. Now we are considering the 4-dimensional space time, so its value will be 4. Then if we take the derivative on both sides, what we are getting is delta of g mu nu into g mu nu equal to delta of 4. Now here we can use differentiation by parts. So what we are getting is g mu nu into delta of g mu nu plus delta of g mu nu into g mu nu equal to 4 is a constant, so its differential is 0. So we will get the value of g mu nu into delta g mu nu is equal to minus of g mu nu into delta of g mu nu. So the value of delta of root minus g becomes, here minus sign is there, root of minus g by 2. You can replace this particular term with this one, that is g mu nu into delta of g mu nu. Now we are going to calculate this third term. Now what is the value of the Ricci's tensor R alpha beta? I am not going to write all the terms here. Actually the Ricci tensor will contains 4 terms. The first one will be some gamma term, then there will be one more gamma term, then there will be 2 terms, 2 cross terms of this gamma. One will be plus and one will be minus. We choose the geodesic coordinates at a point P in V for such that these 2 cross terms are 0. So we can write R alpha beta as gamma of mu alpha mu comma beta minus gamma mu alpha beta comma mu. Then what will be the value of g alpha beta into delta of R alpha beta? It will be equal to g alpha beta into delta of gamma mu alpha mu beta minus delta of gamma mu alpha beta comma mu. Now we make some rearrangements here. It will be g alpha beta into delta of gamma mu alpha mu beta minus delta of gamma. Now I am interchanging the beta and mu. So I will get gamma beta alpha mu and beta, that is I have replaced mu with beta and beta with mu. Now you just multiply this time, then you will get g alpha beta into delta of gamma mu alpha mu comma beta minus g alpha beta delta gamma mu alpha mu comma beta. Let me write this particular equation as a beta comma beta, where a beta is equal to g alpha beta. So this is the derivative of a beta. So in these terms I am just neglecting this beta comma beta That is, I will get G alpha beta into delta gamma mu alpha mu minus G alpha beta gamma mu alpha mu. Actually, when you are taking the derivative of this particular contravariant tensor with respect to beta, there will be one more time. So that is, you have to differentiate it by parts. The differential of G alpha beta comma beta, and here also G alpha beta comma beta term will be there. But for a geodesic coordinate system, this G alpha beta comma beta is equal to 0. That is why we are defining A beta as G alpha beta into delta of gamma mu alpha mu minus G alpha beta into gamma mu of alpha mu. Now, we know that the transformation equation for the Crucible symbol of the second kind is if I am representing one coordinate as x and another as x dash, then I can write gamma dash rho alpha beta will be equal to dou square xi by dou x bar alpha x dash alpha dou x dash beta into dou x dash rho by dou xi plus dou xi by dou x dash alpha dou xj by dou x dash beta into dou x dash rho by some dou xn into delta n ij. Okay, and due to this time these particular Crucible symbols are not tensors. Then what about the delta gamma dash rho alpha beta? When you are taking the variation of delta of Crucible symbol, actually this term does not contains any Crucible symbol of the second kind. So when you are taking delta of this particular equation, this term will be 0. So what you will get is, here there will be one delta time and here also there will be one delta time. Now this particular delta of gamma transforms like a tensor, because remember the Crucible symbols are not tensors, but the delta of this Crucible symbol become a in this particular equation G alpha beta is a tensor and the delta of the Crucible symbol is also a tensor. So this A beta is a tensor. Then in a geodesic coordinate system, since A beta is a tensor, we know that in the case of a geodesic coordinate system, the ordinary derivative and covariant derivatives are equal. So we can write A beta will be same as A beta semicolon beta. This is the contravariant, this is the covariant derivative of A beta. Okay, therefore this particular term, that is G alpha beta into delta or alpha beta, can be written as A beta semicolon beta. That is, it is the divergence of A beta. Then what was the value of divergence of A beta? Then in the previous class we have already obtained the expression for the divergence of a contravariant vector, and the divergence of a contravariant vector is, it is equal to 1 by root of minus g dou by dou x beta into A beta root of minus g. So this third term becomes, that is root of minus g into g alpha beta into delta of r alpha beta. So you have to multiply it with the root of minus g. So the expression becomes dou by dou x beta of root of minus g into A beta. Okay. Next we consider the term delta of root of minus g L m. Here we introduce a tensor T mu nu, where T mu nu is called the energy momentum tensor, such that delta of root of minus g into Lm can be written as some constant k into T mu nu into root of minus g into delta of G mu nu. Okay, here T mu nu is the energy momentum tensor for matter. So now we have calculated these two terms. So what will be the value of delta of root of minus G into R? Its value will be R into delta of root minus G was minus 1 by 2 root of minus G delta of G mu nu into G mu nu. The second term is R alpha beta root of minus G delta of G alpha beta, and the third term was calculated as this one, dou by dou x beta root of minus G a beta. Okay, here you have used the index indices mu and nu. No problem, we can replace it with some new indices alpha and beta. Okay, and then you can take the common terms, that is root of minus G delta of G alpha beta from these two terms. Here there is one minus sign is there, so I am going to write these are the first term, that is R alpha beta minus 1 by 2 into R, then 1 G alpha beta. Okay, plus dou by dou x beta of root of minus G a beta. Okay, so now we can substitute these values of delta minus root of minus G R and this particular term, so that the delta I can be written as delta I is equal to integral over v for it is a 4-dimensional space. Its value is R alpha beta minus 1 by 2 G alpha beta into R into the root of minus G into delta G alpha beta is there. You can take the same term from here also, so you can club these two terms. So plus the remaining terms are K T alpha beta into root of minus G into delta of G alpha beta, plus there is one more term is here, that is this one, that is integral over v for dou by dou x beta of root of minus G into a beta. Okay, now what will be the value of this integral? For example, if we consider integral over x, integral over y, integral over z, dou by dou x of some f of x y z, its value will be simply integral over y integral over z f of x y z. Okay, when you consider this approach here, actually you are taking the here you are taking integral of a derivative, so it becomes the first equation will be same. Here you will reduce one number of coordinates, so it will not be v4 but it will be a 3-dimensional space. Let me represent it with some sigma, so it will be sigma root of minus G a beta into some d sigma, where sigma is the boundary of the 3-dimensional surface. But when we started our derivation, we have taken delta of G mu nu and the delta of G mu nu comma alpha vanishes at the boundary. Then what is the value of a beta? We have defined a beta in terms of the Christopher curvature tensor, Christopher symbol of the second kind. So it will depend on the metric tensor and its derivative. Since at the boundary condition, at the boundary this delta of G mu nu and its derivatives vanishes, we can substitute 0 for this particular integral, so it becomes 0. So the remaining terms will be delta I equal to integral over V for R alpha beta minus 1 by 2 G alpha beta into R plus K T alpha beta into root of minus G delta of G alpha beta. Its value is 0, and its value is 0 when this particular quantity is 0. So we can write R alpha beta minus half G alpha beta into R plus KT alpha beta equal to 0, or we can write it as minus equal to minus KT alpha beta. This is the Einstein's law of gravitation. Okay, thank you.